Some issues. Okay, so then like just now, and I have seen this one mail from Kencho. He has written that you will not be able to send the assignment as of now. So something like that written. You have completed, but the thing is, the assignment notebook is with not means with not with your. So you want to submit when you reach here. Ina, is it like that? Or you all are doing?
Yes, sir.
Others?
We will submit after reaching college, sir.
Yes, sir.
So you can have like that. After reaching here, you can submit.
Thank you, sir.
The other works, meanwhile I will prepare some other works and then you can do it in assignment. Class test and this let us discuss and then we'll do class test, maybe 1 to class test online also. Okay. So now today we'll so we'll see the next continuation to yesterday's one. Okay, so yesterday we had this is the capacitor is connected in parallel with the we have seen this part also. So now let us see the fixed capacitor TC what may be considered, which consists of this variable reactor. So reactor is there, which is actually the current in the reactor is controlled by delay angle alpha method. Okay, so controlling, and then we have seen one is fixed capacitor. Okay, so fixed capacitor. So that is there, and then the overall var demand versus var output characteristics is shown in this figure. So this one. So this is your var demand versus var output. So QL, which is actually inductive var demand. This is capacitive var demand, and this is your total var Q. So if you see this part, And then this is nothing but the generation, inductive generation is more compared to capacitive generation. Therefore, the overall Q is equal to QL minus QC. Okay, so QL nothing but voltage, supply voltage times the fundamental load current at angle alpha. So this is your ILF at alpha. So fundamental inductor current at angle alpha. So the current through this one is actually controlled by this. So this one is this case. So the current we are controlling by ILF alpha. So fundamental current at angle alpha. So you control this. Then QC, since the capacitor is fixed, so there is no controlling part. So this is QC is equal to V times IC. Q is reactive power. Okay, so please remember this. So this Q is actually reactive power. Reactive power. So inductive reactive power demand, capacitive reactive power demand. That is the overall view. So the overall Q is equal to inductive minus capacitive. So inductive reactive power is greater than capacitive reactive power. Therefore, the overall is this. And which is, we are trying to make it unity power factor. No? So that is where we have seen, no? That we can see. Then here, as seen from the figure, the constant capacity watt generation of fixed capacitor is opposed. Actually, the fixed capacity QC is opposed by the variable power absorption. So this is absorption, this is production. Therefore, total watt output Q is nothing but QL minus QC. Then the thing here now, at maximum capacitive watt output, that is when TCR is off, alpha is 90 degree, what happens is, to decrease the capacitive watt output, the current in the reactor is increased. So the current in the reactor circuit is increased by decreasing the delay angle alpha. So capacitive watt output. Now, if the maximum capacitive watt output is at alpha is equal to 90 degrees. So now you decrease alpha less than 90 degree, you will be able to decrease the capacitive output. So you keep decreasing this. Okay, so yeah, you can keep decreasing. So with decrease in alpha, so your QC may reach here, QC may reach here. So then the QL here, that is where it will be there. Then at 0 watt output, the capacitive and inductive currents become equal. So here, when it is at 0 watt output, equal, and thus the capacitive and inductive watt cancels out. Means this, from this formula we have Q is equal to QL minus QC. Yeah. So when QL is equal to QC, means at 0, means when Q is equal to 0, then your QL is equal to QC. So that time these two will cancel out each other. That is so at 0 watt output. Okay, now with further decrease in alpha, so if you further decrease the alpha, what will happen is the inductive currents become larger. Inductive currents become larger than the capacitive current, resulting in net inductive watt output. So this is what this is case. So if you further decrease it, angle alpha, then the inductive current becomes larger. Then so this net output you are getting is inductive in nature. So this is your inductive in nature. Okay, so inductive. So this case, net inductive watt output. So this is the case. Now at 0 delay angle, so at beginning first one was 90 degrees, so the maximum capacitive watt output you will get. Now as the angle decreases from 90 to 0, the TCR conducts current over full 180 degree interval, resulting in maximum inductive var output. Okay, so there. So when alpha was 90, so QC was maximum, right? And QL minimum. Now when alpha is equal to 0, QL is maximum. Okay, so this is what you have. So QL is maximum, and it is actually equal to the difference between the var generated by the capacitor and loss absorbed by the fully conducting reactor. So this you have. So different things. So that is what you have. So QL is greater than QC in this case. In first case, when here it is QC is greater than QL. Okay, so that's this. Then, so these are the characteristics of the FCTCR. Now, next point you have is control of FCTCR, fixed capacitor thyristor control reactor. So it has got 4 basic control functions. First function is synchronous timing, and this synchronous timing is usually provided by the phase lock loop circuit. Okay, so this phase lock loop circuit which runs with synchronism with AC system voltage. Okay, so this is there. So timing pulse. So it is giving synchronous timing. So this one, synchronous timing, synchronous circuit. So it will give you the timing. Time, so synchronous. Then function second is to reactive current for the firing angle conversion. So require that reactive current ILF, this one. So for firing angle conversion, to convert that firing angle, you require that current, reactive current. So in this case, you can have several approaches how to convert that reactive current to this. First one is use this analog function generator. First one is analog function generator. So this is your reactive current. So by using this analog function generator, you can produce this IL alpha, which can be converted to the firing angle conversion. So you convert this one into firing angle. So this firing angle, which is required, firing angle is required for that pulse generator, so that this pulse can be given to the gate of the thyristor. So this is how it is triggering. So how it is starting. Okay, so first time is given, time by the timing circuit. Then this timing circuit will actually actuate this circuit, the reactive current to the firing angle. So it will generate the reactive current, and this reactive current is actually given to the pulse generator, and then pulse generator will actually give it to the gate of the thyristor, where this will be actuated. Okay, so once it is done, so it will be actuated. So the different methods of producing this reactive current is this. First one is function generator is there, one first, right? Function generator. Second one is digital lookup table. Okay, so 2 you have. And third approach is to use a microprocessor kits to produce that reactive current here. Then third function is compensation. Okay, so the compensation of the required fundamental current ILF. So compensation, you can. So this one, this part. So comparator you have. In control system, you might have studied this one. So input current is given, IQ or IC. Then you have this IQ reference current is given. So you minus it, this, then you will get is your fundamental current. So required fundamental current. So it is what you are doing is total output current, IQ, sum of the fixed capacitor and TCR current. Then this is just subtracting the amplitude of capacitor current from the IQ reference. Okay, so this is IC capacitor current minus IQ reference will give. So this is given to the reactive current producing circuit. Then fourth function you have is this firing pulse generator. So this firing pulse generator is actually to main function of this firing pulse generator is to produce the firing pulses for the gate circuit. Okay, so gate circuit to initiate. So if it is diode, as soon as the supply is given and given, and if this diode is forward biased, then it will start conduct. But thyristor nadi, what happens? Thyristor will not conduct even if the power is given, supply is given to the anode, and if this thyristor is forward biased also, it will not conduct unless some gating signals are given, and that gating signals are, we are getting gating signal from this reactive current generation, fundamental, so firing pulse. Okay, so this is what actually you have. So 4 functions. Is it okay? 4 functions. First one is it will produce timing circuit, time, so it will time it, and then at what time it will do, then reactive current will be produced here. This reactive current is given to the firing pulse generator. Then another function is this one, the compensation of fundamental inductive current. Then fourth last function you have is generation of firing pulses. Okay, so thyristor firing pulses, and the main function of that firing pulse is to ignite that gate circuit. Okay, so gate terminal of the thyristor to start. Then voltage current operating characteristics of FCR TCR war generator is defined by the maximum attainable capacity. Okay, so because since the, if you see, you have capacitor here, and then you have inductor, and then this is the case, you have TCR. Okay, so this is your TC. So the current through this is your inductor L. So IL, so this actually here the current is fixed, IC. This current is varied by varying this inductor L, value of inductor L. Okay, so now if you see this, you will have this again control circuit on the gate, this gate pulses and all these things are given. This is how it is, TCR. Okay, so the VI so now here operating characteristics actually is defined by the maximum attainable capacitive and inductor. So capacitive admittance is because of this capacitance. Then inductive admittance is because of this inductor. And by the voltage and current ratings of major power components. So these are the things which the ratings of the power components are, so that is actually as per this. So this is what we have. So this area already we have. This is for inductor. TCR we already had maximum attendance. Then this is your capacitive key. So now inductor. So this is actually nothing but VI characteristics of resistor. You know Ohm's law, no? So like Ohm's law, you can follow this inductance. So it follows a linear circuit method. So linear characteristics. Okay, so this is so then maximum. So within the FCR TCR will operate within this area, this shaded portion. So beyond which the maximum attainable voltage will be up to this, and then maximum current will be up to this. Okay, and then maximum admittance is defined by this way. So beyond this area, it will not be able to operate, only within this. So maximum current it can go is up to this. So beyond this, it will not be able to. So we cannot. So similarly, the BC is the maximum the admittance of a capacitive circuit. Then maximum capacitive current in this area, maximum. So Ohm's law follow behavior, you can use this. Okay, so this is how it is VI operating characteristics of FCR, FCTCR. Then another point from this VI characteristics is dynamic performance of VI generated is limited by firing angle delay control. So you can have that. Means by controlling the current flowing in the inductor. So which actually is results in time lag or transport lag with respect to the input reference signal. So by using this, you can either make it lagging. Okay, so transport lag or time lag in this. So this is what you will have, just general, you can see. Okay, so that is, so from there, if you can find out the transfer function of this, then you'll get this. Then first function of this VI characteristic is to do dynamic performance, and in addition to this dynamic performance, the loss versus output characteristics of the wire generator in practical application is also of major importance. So this dynamic performance we get from VI curve. VI curve. Then the wire generator, the loss versus output characteristics is important when, mainly because in the practical application purpose. So of this TCR, FCR, TCR. So in FC type, three major elements of losses occur. So what could be the three losses occurring in this type? Any idea? Hello? Hello?
Yes, sir.
So any idea types of losses? Seongdo join or Seongdo ji not there? Kilewang Chu, is it there? Is he there? Okay, so any idea, Namit? FCR type wire generator, there are three major elements of losses encountered. So this, any idea for these losses?
No, sir.
Huh?
Idea, sir.
Kezam? Any idea? Hello, Kezam?
Yes. No idea.
Any idea? Types of losses. Major elements. What are the elements, different elements present in this TCR? Kaki. Different elements.
Inductance.
La?
Capacitor and inductance, sir.
So one is capacitor,
Inductor,
inductor, okay. Then other one?
thyristor.
Thyristor. So three. So there will be three major losses. One loss occurring in capacitor, one loss occurring in inductor, one loss occurring in thyristor. Okay, so three major losses occurring in this. So now if you see capacitor or capacity filter losses, so this is actually relatively small, but they are constant. Okay, so like it is like a core loss in machine, so it is relatively small, but it constant, so it will keep occurring. Then other one is reactor losses which is occurring in inductor, that is it increases with the square of the current, means that ILF square, so it increases with this second loss. And then another third loss is thyristor loss, which increases with the current linearly. So these are the three major losses occurring in FC TCR. Therefore, what you can sum up is the total losses increases with increasing TCR current, because see, these are the two main losses occurring, which is actually the linearly proportional to, one proportional to the square of the current, one proportional to the current. Then capacitor is actually constant, so therefore you can just negligible, so you can just see from this. So this is what it is there. So thus the total losses increases with increasing in TCR current and decrease with increasing capacitive VAR output. So it decreases with increase in capacitive VAR output. That. So with reference to this figure, okay, so with this figure, you see, with reference to this figure, you see what it is written here. So with reference to that figure, the VAR demand versus VAR production characteristics arrangement, zero output is obtained. When is your zero output obtained? Hello, this one, zero output. When you get zero output? Any ideas? When you
Inductor
get
and
Q,
capacitance were it seems.
when is Q equal to 0?
When
When
QC is
QL
equal
and
to
QC
QL.
is equal.
So Q is equal to 0 when QC is equal to QL. Right? So that is what you will have. So this means that the current in the capacitor is circulated through the reactor via thyristor wall. So current in this capacitor is actually circulated. So this you have capacitor, then this you have reactor, and this is your thyristor wall. So the current in this IC is actually circulated through this and this, yeah. So resulting in appreciable no load or standby losses. So because of this, no losses. Then these losses, the above losses, decreases with increasing capacitive VAR output, means reduced current. So when you reduce the current here, then current flowing through this one will also reduce. So and then because the capacitive current is circulated via this, so when the current through this reduces, how you will reduce current through this one? By increasing alpha M. Okay, so this is what you have. So this losses decreases with increasing capacitive VAR output in the TCR, and then further increase with increasing inductive VAR output. To produce this TCR current is made larger than the capacitive current to produce a net inductive VAR output. This you can see the loss versus. So this is what loss versus. So linearly, this one I square R, then it will as it reaches here, then capacitive loss is almost constant first case, then slowly, then it will go to what you have. This is fixed loss because of this zero. No? Then after that, inductive loss, yeah. Thyristor loss. Okay, so that is what you know. So now you see this type of loss characteristics is advantage when average capacitive VAR output is relatively high. So in this type of characteristics will be important, especially for power factor corrections. Then disadvantages for dynamic compensation. Okay, so if you want to do the dynamic power compensation, then this one will be disadvantage because the average power VAR output is very low from here. Now next type you have is mechanically switched capacitor thyristor controlled reactor. Next type. Okay, so next type is second type you have is MSC TCR type VAR generator. So in this case, instead of thyristor, otherwise here it was capacitor, no? In first case, it was capacitor here. So now this capacitor is actually, this was not there. In FCTCR fixed, this capacitor was there. Now in this type, fixed capacitor, mechanically switched capacitor is used. And this type of generator is used where less number of switching is required. If more number of switchings are required, then we usually prefer the above first one or the third one, TSC, TCR. Then similar to this, there is a small inductance connected in series with the capacitor. So this one, and tune for the selected harmonics. So this filter key, LC filter. And then the main purpose of mechanically switched capacitor is to generate step reactive power. Step reactive power. So this one, this switch main value, that is one. And if you see the step down transformer is connected here from grid to state, then the main purpose of this step down transformer is to match the rating of TCR, because TCR rating may not be like, say, suppose if it is 60 or 33 kV here, then the TCR may not be rated at 33 kV, so it will be less than 33 kV. So in order to bring it to the required TCR rating here, we use this step down transformer. So purpose of this step down transformer is to match the rating of TCR. Then TCR, this performs a controlled reactive power absorption when there is an excess VAR generation. So whenever there is an excess generation, then it will absorb it whenever absorption is there in a controlled manner. And then this another point you have is almost the rating is almost equivalent to the single mechanically switched capacitor rating. Then how you can do is, how you can control this reactive power absorption is as per the requirement of the reactive power generation. Number of switches is on, so you can put on the number of switches depending upon the requirement of power generation. For less reactive power generation, less number of switches on. If it is more, then more number of switches on, so you can connect that switch more and less. So the second type, that is there, and these are actually rarely used, just for the purpose of understanding we have done. So FC TSR and then MSC TCR are rarely used in the practical application. The most commonly used are this one. So this is the most commonly used type of SVC for the VAR compensation. Okay, why it is more commonly used? This one. Hello. Ugen Funso or Ugen Wangchu. Why this thyristor switch capacitor, thyristor controlled reactor is most commonly used type?
Maybe because of fast switching action
Fast switching action
of the thyristor.
Any Tenzin Jamso? Any? Yesterday only I told, no, out of three, the third one is used, most commonly used because of
Smaller rating reactor is required, sir.
Smaller rating of the reactor is required,
Yes,
which results in the less generation of harmonic. So that is why we use this TCS. So main harmonics is actually the enemy of one power system network. Enemy. So now because of this actually smaller ratings are required. This thyristor rating required in this one is small, or this reactor. So here the rating is small rating, which results in the less harmonic generation. Therefore, we usually prefer this. Okay. So the primarily the switch TCSR, TSC TCR is developed for the dynamic compensation of the power transmission system, dynamic, and with the intention of minimizing the standby losses and providing increased operating flexibility. So these are the two main objectives of the main purpose of power dynamic compensation with the intention of minimizing the losses and increasing the operating flexibility. So the basic single phase TSC TCR is shown in this. So this is there. Okay, so this is your, what is this? Hello, Sonam?
TCR.
TCR, this is TCR. So TCR is there, okay? Then for FC TCR, you had fixed capacitor here, right? You know FC TCR, you FC fixed capacitor is connected in parallel with TCR. Then a mechanical
Yes,
switch,
sir.
you will have this one mechanical switch parallel with it. So now for thyristor switch capacitor, you will have this is your thyristor switch capacitor. TCR is this, or not TCR, TSC. This is your TSC. This is your, so number of TSC is connected in parallel with inductor. So depending upon the type of compensation you are going to do, so here the construction wise, have you seen construction? Everything same, okay, everything remains same. Only thing is TCR will remain same permanently here, others will change. If it is fixed capacitor, you will connect fixed capacitor. If it is mechanical switch capacitor, then you will connect one mechanical switch here. Now here you are connecting is, this is your, this block is, what is this block? Poonam, what is this for? Hello, Poonam? Banking them na Poonam.
No, sir.
Poonam, so what block is this? Is TSC block, okay? This is TSC block, this is TCR block. Okay, so TSC, the TSC block there. So that is there. So for a given capacitive output range, it typically consists of n TSC branches and one TCR. So this is your, and this is your TCR. Okay, so that is what you will have. Okay, so with this, we'll stop here. The work and the characteristics that we will continue in next class.
Okay, sir.
Thank you, sir.
Yeah,
Thank you, sir.